What do you got for me? What do you see? Midpoint, yep. That's a midpoint of like this segment right there. Right? That's true. We got squares and rectangles. Rectangle here, square there. Now, are we going to get a number for the area? No way, right? Because we have no numbers anywhere, so what we're going to get is like a proportion, right? So if the square were, 3 by 3, then the rectangle inside it would be bigger. We get a certain area, right? But if it was 2 by 2, right, the rectangle would be smaller, and we get a different area, right? So it's all going to be in relation to how big the square is. So if you wanted to figure out what the area was, what you probably want to do is call these sides x, because it's a square, right? And then solve from there, and you get an area in terms of x, right? It would be in terms of numbers, right? But it would be in terms of this variable. So maybe it'd be half of x, maybe double of x, something like that, right? Some way that relates to x squared. But let's forget about that for now. Let's talk about what you see and what you know. Zayden.
The long sides of the rectangle are going to be the same.
Yep. So these guys are going to be the same length, right? Because rectangles have congruent sides, opposite sides. What else?
Same for the other side.
Same for the other sides. Same as it ever was. All right.
We got some triangles.
Yep. What else you got for me?
We got some triangles.
We got triangles everywhere. What about them?
Do we know if they're right angles?
We do. These are right angles. Why?
Because they're 90 degrees.
Why?
It's a square.
Because it's a square. Just because it looks 90 doesn't mean it is.
Yeah, because you always make those diagrams fake.
Yeah.
What else we got? Thing.
Because of that, we can use HL to get the smaller triangles congruent to each other as well as the larger.
So check it out. Small triangles are going to be congruent by HL. Do you guys see that? Hypotenuse leg, right? Hypotenuse leg, yeah, congruent. Hypotenuse leg, right? And then same thing with the big triangles by hypotenuse leg. So we know we have these congruent triangles. So we figure out the area for 2 of these, and we get the area for these. We can find the area of the rectangle by subtracting them from the square, right? My question is, how do we get that area? Where do you see vertical lengths?
Like on your left side, left line that goes up and down.
Nope, those aren't vertical.
Yeah.
Right, it's got to be an x. No x there. That's a linear pair. Like, well, it's not even a pair because there's 3 of them, but those are all going to have 1/8. Right? They will be supplementary. That's true. Zayden, what else do you see?
We could do CSP to get angles for the big triangles and then 90 degrees, and then use linear pair theorem to get the
That was like the first step.
2 of the angles for.
All right, Danny, shut up.
And then AA to get those 2 different triangles similar.
Yep, so these 2 angles are going to be the same by CSP, or CCP, we should say, right? And these 2 should be the same by CCP. And I think you guys know that a rectangle has 90-degree angles, right? And we know whatever this angle is here must add with these 2 make 180, right? Does that make sense? Right, this guy plus red plus green, it's going to be 180. Well, isn't this guy equal to red and green? Right? 180 minus red and green gets this. 180 minus red and green gets that, so these angles must be the same. So that goes there and that goes there. Same thing with the green down here, right?
Yeah.
Cool. So these are congruent, these are congruent, but what else do we know?
They're also the same.
So these 2 are similar, or like all these are similar, I should say. So let's use pink. All of them are similar. Okay. So sides should be proportional. If you want to solve the rest of this at home, again, if this is x, figure out the rest. We're going to stop for now, okay?
TF.
There'll be more tomorrow. We're not going to be correcting our, grading our quizzes today. Here's the plan. I will give you 1 more go at it, meaning that if you want to come in at some point during, before, after school, I don't care when, as long as it's not during this class, right, my class where I'm teaching you. You can come in during another class, that's fine, sit in the back. I'll give you a quiz, and you can finish it up. Okay? Now, before you come and finish it up, you should study up. Okay? Watch the videos a couple times. I'll give you one shot, meaning don't be like, I'll be here after school for 10 minutes. And then shut up. So I'll be here after school for 10 minutes. And then I'll come back on Tuesday for 10 minutes. I'll come back on Wednesday for no, we're not doing that, right? One shot. Like Eminem, right?
I know
Say
that
it.
song.
Do not miss your chance to blow.
No, come on.
You don't know the song?
The beginning.
You better lose yourself.
If you just had one shot.
You better lose yourself.
The most gangster person in the school. What did you just say? And one opportunity. If you have one opportunity, what?
One chance to blow.
I
Take
think
it.
if he goes,
We'll just let it slip, right?
Let's go.
Mom spaghetti.
palms.
I need to be on it.
Right. Okay, thank you.
Wait, so Matt.
He's
this
nervous.
entire-
The Weird Al version of that song is just as good.
On the
That's
surface, he
amazing.
looks calm.
Unforgetting.
I don't like the same thing for all of them. I have no idea.
Dedicate to it.
Straight
Hey,
up.
we should play like Godzilla.
We had John Coltrane. Maybe we'll do Eminem
I can
tomorrow.
do. Have you listened to Godzilla?
No.
Oh my
It's a
god,
good song,
you're
man.
insane.
Is it good?
It's insane.
Really? Because like the last 3 albums have been garbage.
Breaks the record
Oh.
for the most words per
Yeah,
minute.
he broke the record for the most words per minute. Yes.
Like 230 words in
Yeah,
Boy, still got it, huh?
This,
Wow.
this album's good. I can sing it. I can do
I'll
that
check
part
it out.
too.
That's
I can do that
incredible.
part.
We got something for you. But yeah, that's what we're doing. We're going to grade the quiz on Wednesday in class because we have early dismissal. I'm still trying to figure out how the school schedule works, how best to construct the way we do things in class. I'm thinking when we have early dismissals from now on, if there's a quiz to grade that week, that'll be the day we do it. What?
So we can come in Tuesday or Monday?
I'm coming in.
Cool.
I remember that.
You know what?
Circulation, like, I'll be fine.
I'll come with you. That's good. I love you, Davey.
We'll just put him back.
Davey,
That's clearly the answer. Put him back. That is obviously exactly what you're supposed to do.
For you. All right.
A lot of people think maybe you should.
So, we are continuing what we did last week, right? We talked about these different segments like perpendicular bisectors, angle bisectors, medians, all that jazz, orthogonals, right? We talked about their special centers. And we assumed last week, because we went on GeoGebra, right? And we assumed that they'll always intersect at a certain point, right? They'll always be concurrent. And if they're always concurrent, then those centers will always exist for a triangle, so we can find those centers. And those centers will tell us special things about the triangles, like a circle inside and all that crap, right? Now, we assumed, basically, based on GeoGebra, a lot of anecdotal evidence, right? All the triangles that we made, look, all the angle bisectors are concurrent, no matter how I move the triangle. All the perpendicular bisectors were concurrent, no matter what I did to the triangle. All of the medians were concurrent. All of the orthogonals were concurrent. So, this week, we're going to actually prove that they are concurrent. And that takes a little bit of doing. So much so that we are introduced to our first lemma. We've used lemmas before.
I didn't get it back. Hey.
This is the most
We've used lemmas before, but we've never really called them that because they've been so small they weren't worth mentioning. A lemma is something that you need to show your audience. Yep, that's nice. You need to show your audience that, hey, this is true, right? I'm not trying to prove this. This is my point. This is not what I'm trying to prove. This is not the theorem I'm trying to prove. But here's something I need everyone to understand before I actually go into the proof, right? We've done like stuff like that plenty, right? I've drawn some example triangles. We've done that all the time. This is a lemma, meaning that I'm going to prove that this is true. That way when I use it later in a proof, you guys are going to go, oh, okay, I see. And the reason we're going to do that is because I consider this pretty counterintuitive. Look at that. It says if A over B equals C over D equals E over F, then we should be able to say that A minus C over B minus D should equal E over F. And this does not look intuitive. It's like, if I have this, then I got that, right? If I jump straight to that in a proof and I said, just trust me, right? You'd be like, wait, what? What? How? Right? How are those related? Right? If I try to do A over B minus C over D, I don't get that. Right? I gotta get common denominators and stuff. Like, how in the world? What? Right? So, I'm gonna prove that this is true. That way when I use it later, to prove that things are concurrent, you won't freak out about it. So here's the idea. What does this mean? Well, we've been dealing with this stuff all the time, right? We've been talking about how sides are proportional, right? And they're all related. Now, they might be different numbers, but they're all related the same way. Remember, division shows relationships. So if I choose two numbers like 6 and 3, how are they related? How are 6 and 3 related? By half or double, depending which way we go, right? If I write it like this, it shows you the relationship between 6 to 3 is double, right? Does that make sense? If I flip it, it shows half. But in general, division shows relationships. You want to know how two numbers relate? Use division. How do 7 and 3 relate? 7 is 7/3 of 3. Does that make sense? Right? If I relate them, right, proportionality shows relationship. So how does 7 relate to 3? Well, it's 7/3 of 3. How does 3 relate to 7? It's 3/7 of 7. Do you see how silly that is? I mean, it's obvious that it is once you get the idea. But if people just go, oh yeah, proportionality shows relationship, you use division signs. And you're like, I don't know why we use division signs. Right? Why? Well, the reason is because if you write it in division, it shows the relationship. How does 6 relate to 3? By double. 2-to-1 ratio, right? Do you see how when you write them as a proportion, it shows you how they relate? Right? That's the idea. So if this works with any single number, right? That's what A, B, C, D, right? They're all variables, right? They work with any numbers, right? As long as they're equivalent, this is true. It should work with specific numbers. So let's experiment with specific numbers so you get an idea of what this is saying. So let's start with 6 and 3 for A and B. Now, I need values for C and D, and they can't just be anything, right? They have to be equivalent to 6/3. So what numbers for C and D can I use? Well, I could use 6 and 3 again, but that wouldn't be very interesting.
You can do 10 and 5.
I can do 10 and 5, because they relate by double. What other numbers can I use? 14 and 7. Ooh, 14 and 7. We're getting creative in this class. All right, so those are my numbers for A, B, C, D, E, F, okay? Is this true? Yeah, 2/1, 2/1, 2/1. They are all proportional. We cool with that? They all have the same relationship. A, B, C, D, E to F. So what I'm going to show now is that if I take those same numbers and plug them in here, this will be true. You ready? A is 6, and C was 10. B is 3, and D was 5.
Yeah, that's funny.
And that should be equal to 14/7, right? Now that's not how you do math. You don't subtract those like that. You need common denominators, right? That's not what I'm saying. I'm just saying that, fun fact, it works. As long as they're equivalent fractions, right? Then you can do that. That's kind of cool. So is 6 minus 10? It's -4. 3 minus 5, -2. Is that equivalent to 14/7? Well, -4 divided by -2 is +2. And 14 divided by 7 is also 2. So yeah, that checks out. This only works for equivalent fractions. You can't do this anywhere in fractions. You can't just subtract 2 and have them equal to 3rd, right? That doesn't work. They all have to be equal to each other to start out, okay? And this works. And now I'm going to show that it works for any numbers, not just the numbers I chose, okay? Now again, they have to be equal first. You can't just pick 3 random fractions and have them equal to each other. It's not how, it's what? No. Okay? It's when they're all the same fraction. You can take the first 2 and subtract them to get the 3rd. You can also add. Right? 6 and 10 adds up to 16. 3 and 5 makes 8. 16 over 8 is 2, right? So adding them would also work. I'm interested in the subtraction one because that's what we're going to do later. Remember, this is a lemma. I need to prove this. That way I can show you it later in a theorem, right? It's a specific case. So this is not what we're trying to prove, but you need to understand this concept. So here's what I want. I want this. If I start with this, I get that. Okay? Now, this is going to be hard to do because I really don't know where to start. If you don't know where to start, one way that you can start going about problem solving, we know many ways, right? Find a similar problem that's related, et cetera, right? One of the ways is start from the end and work your way backwards. We know what we're trying to get to, right? So before I even start, I'm going to take this equation here and I'm going to mess with it. Because if I mess with it, I might reveal what I need to get. Check it out. I'm going to get A and C on their own. Right? I'm just going to move some stuff around, right? We're doing algebra. I'm changing the problem a little bit, like I'm moving the stuff around, right? Not changing the problem, but making it look different, so I can find an easier thing to look for, okay? So what I'm going to do is I'm going to move over this. Now, if this was A minus C divided by 2, how would I move over the 2? If it was A minus C divided by 2, I would multiply by 2, right? Now, it's A minus C divided by all this junk, but if I want to get rid of all that junk and move it over, I still multiply by that. Now there's 2 terms there, so you need to wrap it in parentheses, right? Okay. So what I'm going to do is I'm going to do this. And again, as long as I wrap it in parentheses, I can move all that at once by multiplication, okay? It's that idea. We're going to treat that whole thing as a number, right? Divide by 2, I'd move by multiplying by 2. So I treat that whole thing as a number. Whenever we treat something as a number, we call it a quantity, right? we wrapped in parentheses. So I treated the whole thing as one number and moved over by multiplication. Now I think you'll agree that this is multiplication, right? E divided by f times quantity b minus d. So when we multiply by b minus d, it goes on the top, right? Multiplication happens from the top, division happens from the bottom. So another way to write that would be this. Right? Is everybody cool with that? So really what I'm trying to show here is that if I can find out what A is, and I can find out what C is, right, from up here, if I can find out what A is and find out what C is, then I can set them up in subtraction and hopefully mess around with the algebra and get here. And once I get here, I can work backwards to get what I want. Does that make sense? So I want to find out what A is and find out what C is. That's what I want to do. Okay? So let's actually start doing the proof. We're given this. A over B equals C over D equals C over F. Now, I know I want to get to here, but really what I want to do to get to there is get to here first, right? Find out what A and C are, plug them in, and I'll get stuff, okay? So we want to get A and C on their own. Now, I want A and C. So these are the parts with A and C in them, right? Now, AB equals two different things. I want something with E and F in it. Okay? So I'm going to use the EF one. And I also want EF over here. I think you see where this is going. So I'm going to use math and multiply over and get EB over F. And C equals EB over F. This is kind of like the Pythagorean theorem one we did, right, where we got A squared and B squared on their own. Now that we know what A and C equal, kind of like when we knew in Pythag what A squared and B squared equal, we can add them together, right, and figure out what happens. In this case, we're going to subtract them. Does that make sense? I'm going to take what I know, and I'm subtracting. So I'm going to write A minus C equals. Now, by substitution, what does A equal? What did we find out A equals?
C.
EB over F. Right? Now I'm supposed to subtract that from C. What did we find out C equals? ED over F. Okay, okay. Remember, my goal is to get to here. Because then once I get there, I can work backwards and get to what I want, right? So I'm here. Don't they have common denominators? Right? If I had 2/3 and 1/3, you could put those together, right? This is something F's, and this is something F's. I don't know how many F's, but it's some amount of F's. All over F, right? Common denominator. EB minus ED. Right, if that was 2/3 minus 1/3, you could subtract them and put them together, right? So I did EBFs minus EDFs, right, is whatever this is of F's. Does that make sense? Some number of F's minus some other number of F's is whatever this is F's. And no F's were given. I'm going to pull out E from this, and now I'm here. I pulled out E, right? And if you notice, I'm on my way, right? You see that? And now I just work backwards. I'm going to divide by B minus D and move it over. If it helps you, this can be written the same way. Right? That's the same thing. Multiplication, right? Still done on top. It's fine. Then I divide by B over D and I get this. And I win. Yep, so I got A on its own and C on its own. And then I said, well, if I know what they equal, I can subtract them, right? And then I move stuff around. That's it. Yep, true for any set of numbers as long as the fractions are equivalent to start with. You can do that. Okay? Yeah?
So, do we actually have to do this on the test? Is this? Are we just doing this once to prove that?
This is part of our lemma, which means you need to know that this property exists, right? Will I ask you to prove that? I'm not sure yet. I'm leaning on the side of no, but in theory it could be easy points. Like, none of this was necessary. All you have to do is set A, B equal to EF and CD equal to EF and move stuff around, right? So in theory, it can be 3 points. Are you feeling 100% about that right now? No, but you will, okay? This is one of the easier
I'm
things.
really bad at algebra though. I miss numbers.
Right, and that's another reason why I want to test it. But in general, right, set them equal, move them over by multiplication, right, subtract them, do your thing. So do you guys see that this is true? Cool. We need that for our proof. Move on to the next page. Our next lemma, the next thing you need to know, is that the area of a triangle is always proportional to its base and its height. Area of triangle equals base times height over 2, right? We cool with that? Now remember, proportion means that they're related. They have a division bar, right? We have like something like this. A over B equals 2, right? That means that how do A and B relate? Double, right? 2 to 1, right? I'm saying that the area of a triangle should relate to its height. That's the relationship. The relationship here is 2. The relationship here, I'm saying, has to do with height, okay? There's a relationship there, and we know that, right? More height, more area, right, in general. So look as I take area of this triangle, and I rearrange it. Right, I moved over the 2 by multiplication, divided by h, and b is on its own. So I'm saying the relationship between the area and its height is the base. That's how they relate. If you take the area of a triangle divided by its height, you get the base. Well, doubled, right? I'm going to move that 2 back over just to show you that, look, this relates by some number. B over 2 is some number, right? If B was 10, the number would be 5, right? The relationship is whatever the base is divided by 2. I can also do the same thing with height, right? They're proportional. They relate. So if area is 6 and height is 3, then the relationship is 2, right? So B would have to be 4. You know what I'm saying? If that's 6 and that's 3, what's 6 divided by 3? 2. And so B would have to be 4. Do you see, if you know how they relate, you can figure out what B is, right? Vice versa. This should not be shocking. We can find the base if we're given the height and area, right? We can find the height if we're given the base and area, right? There's a relationship here. The area is related to its height and its base. Now,
But it's not
interesting-
always 2, right?
It's not always 2,
Yeah.
right? But this will always be 2. That 2 always there, because remember it's half base times height. That's the area, right? So that's where that 2 comes from. Okay. Oops. Move this back over. Right? You cool with that? Move over the H, we get the same thing. Move over the D, we get the same thing. Right? Okay, cool. All right, so here's the point. Here's a triangle. In fact, how many triangles do you see? 3. 1, 2, and 3. We have a small, medium, and large triangle. Now, are these triangles similar? Are they congruent? What do you think I'm trying to show here? Well, if we look, can't prove they're congruent. We have no information, right? Similar? Maybe they have shared sides or angles or something? No, not really. You might be like, oh, look, this shares an angle, right, with the whole thing. But that's only 1, right? So we're not going to be able to prove these similar. And that makes sense, because you can imagine that this triangle could be equilateral and this one isn't, right? And if that's equilateral, there's no way it'll be similar to this if it's not equilateral, right? So we're not going to show they're similar. We're not going to show they're congruent. What we're going to say is that this triangle, its area should relate to its base. And this triangle's area should relate to its own base, right? And then the big triangle would relate to the whole base, C plus D, right? So we know this to be true, right? That's one of our lemmas, right? We know this to be true. Now, what is the area of this triangle here? Let's call it triangle ACD. What would the area of that be? Well, it's going to be half base times height, just like any triangle, right? Half. What's the base for this triangle right here? Little c, right? So base is c. And our height, oh, we don't have that. We should put the height in. Isn't this the height? Right, more or less. That's the height. H. can do it here if I want. It's fine. There's a reason they did it on the outside. Let's talk about this small triangle here. Okay, so we get the area of this one. Let's talk about the area of this one. Let's call that triangle BCD. Area would be half, right? What's the base of this one? Little d. What's the height of this triangle? Well, is it the same as this one? Because if it's not, we can't use h again. It is the same height, isn't it?
Whoa.
Do you see how, because both triangles are inside this triangle, they have the same height? From here to here is there. From here to the top is still there. These triangles have the same height. The blue triangle and the green triangle have the same height. This will always be true for any two triangles inside the same triangle.
But you can angle it and then it would get longer, right? Like if you move D over.
Even if I moved this, right, or moved this, the height would still be the same for the two triangles. Right? Now, that height might change, but it's going to change for both, right? See what I'm saying? If I move that down, it changes the height for
I was
both.
looking at the wrong two triangles.
So the two triangles here and here, the blue and the green,
Yeah.
have the same height. So when I want to show how their heights relate, right, I do division, right? Ignore these equal signs for now, okay? Right? Isn't that the same as that? And that the same as that? Right. Ooh, I forgot the h. Same height?
That means, you know,
Yeah.
proportional.
So what's half divided by half?
One.
1, right? What's h divided by h? Since they're the same height, they divide out, right? H divided by h is 1. If they had different heights, this wouldn't work, right? What's 1 times c times 1?
C.
C. So how do their areas relate? Well, they're proportional to their what? To their what are C and D? Are C and D the heights?
The base.
The bases, right? Now, could we do this with the height? Sure. You just turn the triangle on its side, the base becomes the height, right? So this is our lemma. The area of a triangle is proportional to its bases. So if you compare two areas, they're proportional to their bases.
So that means 1, 2.
So if this area was 8 and this area was 4, how do the areas relate? Half, right? Which means that if this side were 6, this side would have to be,
So what?
try again, half. 3, right? So just by knowing the areas, I know how their bases relate. So if I told you the area was 24 and the area was 6, they relate by a quarter, right? So this is 4, then that's I get this one for free. It has to be 1.
We have the area.
It's a 4 versus 1. Okay? So if we know the area and we know one of the sides, we can get the other side for free. That's pretty neat. Because then we know the whole base is 5, and we know the height of the big guy, right? We can figure out the area of the whole thing.
Wait.
We can do all kinds of crazy stuff, right?
So that's if.
So if I knew that this was 24 for the area, and I knew that this was, I don't know, 3. Area is 3. And I knew that this side right here was, let's do 8. Okay? I'm making the numbers nice, but they can be anything, right? How do 24 and 3 relate? What's their relationship? Well, if you don't know it off the top of your head, divide it, right? That's how you find the relationship. What's 24 divided by 3?
Oh,
8. The relationship is times 8, right? Depending which way you go, right? Divide by 8 times 8.
oh, then that's it.
So that should be the same relationship as this. Their relationship was times 8,
Oh, then
right?
you're fine.
So their relationship should be times 8. So if this is 8, we're going to divide by 8 because we're going to small, right? What should this be? 1. Right? It's because their heights are the same. If their heights weren't the same, we'd have too much going on, right? Who knows, right? It's because their heights are the same. Otherwise, it'd relate to their base times their height. And it's like, well, duh, right? That's not interesting. We know that. So area relates to its base as long as the triangles have the same height. You with me on that? So we have two lemmas. Lemma number 1, this means this. You can go from that straight to this, okay? Lemma number 2, if the height is the same, then the bases are proportional to the areas of the triangle. Okay? So that's just given. You cool with that? One more thing we gotta do. We need to know definition. A Cevian. It's a fun word. Any segment that connects a vertex of a triangle to its opposite side. Okay. So let's draw an example. That's a triangle. Why do we call it a triangle?
Because there's 3 angles.
3 angles, very good. And the vertices of those angles are here, here, and here. So if I draw a line from any of those vertices to its opposite side, that line is a Cevian. Is it perpendicular? Is it bisecting? Is it bisecting? I don't know. I don't care. It's a Cevian. A Cevian is just a general term for any of the things we were talking about earlier, right? Perpendicular bisectors, angle bisectors, right? Stuff we learned about last week. It's the general term. Anything from a vertex across. That's a Cevian. Right?
This is a general term. I'm sorry.
So Cevians is a general term for an angle bisector. Because doesn't an angle bisector take a triangle and go from the vertex across, cutting this in half, right? That's a Cevian. A median is a type of Cevian because it goes from a vertex across the other side. And what does it do to the other side? Cuts it in half. It's a midpoint, right? Midpoint to vertex. You guys remember that with medians, right? So a median is a type of Cevian. So we have angle bisectors, medians. An orthogonal is a type of Cevian, right? It's just a Cevian that hits the other side at 90, right? Now our last one is perpendicular bisector, right? You might think a perpendicular bisector is a Cevian, and it can be, right? That's a perpendicular bisector. That's a Cevian. But can a perpendicular bisector also be this? Here's the halfway point. Straight up at 90. Right? This triangle's moved over a little, so it ends up not going through the vertex. Right? Remember those can go off? Right? They're kind of weird. So sometimes a perpendicular bisector is. Other times it's not. So we don't consider it a Cevian. Right? Here's a better example. Here's a triangle. Halfway point's here. Perpendicular bisector's there. Not a Cevian, right? Doesn't go from vertex to the opposite side. We cool with that? So perpendicular bisectors don't count. But Cevians are any of these 3. They're just special Cevians, right? Cevian that bisects an angle, a Cevian that cuts the side in half, a Cevian that hits the other side at 90, right? That's what these are. Alright, so here's the theorem, and this is what we're going to prove. Ceva's theorem. Ceva is the thing that Cevians are named after. Okay. So look at this triangle. Do you guys see that AE is a Cevian, right? Vertex opposite side. Do we know if it bisects the side? No. Do we know that it hits at 90? No. Do we know that it bisects the angle? No. It could be one of these, or it could just be a regular Cevian, right? It's basic, and that's okay. It's okay to be basic. BF, Cevian. CD, Cevian. So we have 3 Cevians that are concurrent. See how they all intersect at one point? Right? Now we know what happens when we have 3 bisectors that are angle bisectors that are concurrent, right? We get the incenter. We know what happens when we have 3 medians that are concurrent. We get the medicenter, or centroid. Orthogonals that are concurrent. Orthocenter, right? So could this be one of those? Maybe, right? All I'm saying is that these 3 are concurrent. So if we have 3 Cevians that are concurrent, then this should be true. Check this out, this is weird. Then A over B times, not equal, C over D, times E over F equals 1. So here's what that means. This length times this length. Or sorry, this length divided by this length. Times this length divided by this length. Times this length divided by this length equals 1. Always. If they're concurrent. If they're not, if this line goes over to the side and doesn't hit all there, right? If this doesn't happen for our 3 lines, right, and this happens instead, right? but they intersect here, and then this guy misses, right? Then this wouldn't be true. But when they are, it divides up the triangle in such a way that if you take the relationship here and multiply it by the relationship here and multiply it by the relationship there, you get 1. Now let's think about what that means. Let's pick a number for A and B. Give me a number for A and B. Preferably even numbers. 4 and 16. Okay. Now we want to multiply that. Again, I'm just checking it with numbers, okay? Where it equals 1. Now, what would I have to multiply 4 over 16 by to get 1? Well, if we have a 4 in the bottom here, isn't 4 divided by 4 1? That's good. I could put a 16 here as well, and that would make 1, right? Now, hold on. Hold on. I don't have to put a 16 there. I can put a 16 here. Do you have 16 divided by 16 is 1, and 4 divided by 4 is 1? 16 divided by 16 is 1, right?
Yeah.
4 divided by 4 is 1?
4 is 1. Was it 16 divided by 4 is not?
Oh, sorry. Thanks for calling. Thanks for catching that.
Oh.
Now, if these already equal 1, what kind of numbers have to go here?
16 and 4.
Nope, if I put 16 and 4, these become 1, and 16 divided by 4 is 4. We get 4.
They have to be smaller numbers, like on top, or
The same
what?
numbers.
The same numbers.
Same.
Pick a number.
4.
Pick a different number than 4 and 16.
14.
Hold on, what do you say?
I thought we said the same numbers.
Will that equal 1?
Oh, the same.
Will that equal 1?
14.
That's what you meant.
That's, yeah.
They don't have the
Will that equal 1?
I don't think so.
I meant
14 times 15 times 16 divided by, sorry, 4 times 15 times 16. I said 14. 4 times 15 times 16 divided by 4 times 15 times 16.
Yeah.
Yeah, they'll equal 1.
Okay.
So as long as these are the same, or at least equivalent when you simplify, right? Then this equal 1.
So you can just pick a random number to put there. Is that how that works?
This will always be true. This will make a triangle that divides up in that way. So this is what this means. It means if these are Cevians and they all are concurrent, then A and B and C and D and E and F, if you arrange them in this way, they will equal 1. That's one possible set of numbers that will work for this, right? But notice it doesn't work for just any, right? If I put a 6 there instead of a 15, would it work? No, right? If I put a -4 here instead of a 4, would it work? No, you get -1, right? So there are only a certain set of numbers that work. All numbers work, right? But only a certain set at a time. Does that make sense? When you have a locker combination, every possible number on there could work, right? Now, will all of those numbers work to open the locker? No, a certain set will for each lock, right? Same thing here. You can put in any numbers there and it'd be true, right? But they have to be a certain set, right? You're allowed to put in any numbers, but once you have one number locked in, it kind of locks in your rest, right? So here's what we're going to do. We're going to prove this theorem, that this is true, because this is super useful, right? We can prove that lines are concurrent using this if we use the converse of it. If this is true, then this means they're concurrent. If this is true, then that means our guys up here are concurrent, right? That's what we assumed last week. Here's the triangle. Nope, we're not done. So all we know is that they're concurrent. They do intersect at one point. And we know they're Cevians. We're given no other information. Now, guys, shut up. The lemma that we had before, we had 2 of them, right?
Right.
I'm talking about the one that we had a triangle for. Do you guys remember that lemma?
No.
That lemma is this. If the heights are the same, then the areas relate to their bases, right? Do you notice any triangles that have the same height in this diagram? A lot of them. Do you guys notice that this triangle here, ACD, has the same height as BCD? So the area of ACD should relate to area of BCD in what way? A over B. Their bases. So the area of triangle ACD divided by the area of triangle CBD should relate to their bases, right? What's the base of ACD? Little a. Thank you, Jess. What's the base of CBD? Huh? Little b. All right? Now, what other triangles also have base A and base B and the same height?
Like half.
These two have the same height. Don't they also have the same base? So it must also be true to say that triangle ADG, its area, and triangle BDG relate to their bases, A and B. I'll see you tomorrow.
What's the other one?
I think you might see where I'm going here, some of you. If you want to correct your stuff, make sure you come back with your A game. You get one shot. Did you take it or just let it slip? Okay.